The person from data sciences is there, she's not here.
This meeting is being recorded.
Hello? Okay. Go ahead, you can hear me now?
Yes, you're audible.
Okay. So it's being recorded, so that's fine.
So your voice is a bit faint. Is there anything you can do about it?
Say that again? I didn't hear
Your
you.
voice is a bit faint.
Well,
Oh yeah, it's clear now. No problem.
is it better now?
Yeah.
Okay, maybe I'll have to keep this close. That so tell me, kind of point out when you can't hear me. Yeah.
Sure, sir.
Okay. Yeah. So how many of you are from data sciences here? So there was this 1, 2 of you, or 3 of you. So you were not there the last. You were there. There was this one lady who was here, who was there last time. I thought that she was from data sciences. Do you know? Okay, so there are still 3 of you. So you have not taken any logic course, like a discrete math course. Do you know what Boolean algebra is? Yeah. So you know Boolean functions, or a little bit, sets, functions, and things like that. Okay, so the rest of you, I'm assuming you have had a logic course, correct? Because you are from CS, either at the MS level or BSc level, correct? So you have had a logic course. But you are from CS, but you did not do a logic course. Oh, I see. So for BSc CS, logic is not a requirement, is it? Only for MSc it is. Okay, but theory of computation you have done. Without a logic course, you have done it, but I guess you have discrete math thing. Okay, so most of, but you're doing it simultaneously, but you're not doing it because it's just an elective, yeah? Okay, so that's okay. So I'm just saying, so some of you, for Jessica, for you it will be, repetition, but maybe this is a little bit slightly different perspective. So I stress more on the modeling, how you use logic to model artifacts. Okay, so that is one aspect that you will have to find out, and how you can use this Z3 theorem prover to not only model your artifacts and your property that you want to verify, how you could coax the Z3 theorem prover to, prove certain things that you want to prove. So that is something that I would certainly expect that you will be able to do. Okay, that is one. And the other thing is you have to have an understanding of what the most important basic concepts that you'll be using. That I'll introduce it to you. And when you read some of those papers, a little bit of the notation you can always kind of get acquainted with, but certainly certain concepts, etc. But I'm not sure that I can, in the two lectures that I cover, I won't be able to, I must confess that I won't be able to cover all the concepts, so which means that you will have to overcome some of the gaps in logic when the paper that is assigned to you that you will be reading uses those things. But that is when you will have to, yeah. So, you have to make up for it by either reading a little bit of supplementary material as if you like, I mean as necessary, and we are always there to discuss before your presentation about to help you understand those papers, so that I'll have to be worried. So I'll go slow here. Okay, so what is logic? Okay, and this one is too small, I guess, so I'll make the font a little bit bigger before I switch over to the this is better. You can read it. Yeah. Okay, there are various different kinds of logics. Okay, they are differentiated in terms of how expressive they are, what kind of properties that they can capture, and so on. One of the simplest kind of logic is what you call as Boolean logic, or sometimes it's also called propositional logic. So this one is works in this domain where where the variables there can only are propositional variables, or Boolean variables that can take either true or false values. And this kind of logic is, in general, logic has been used, philosophically to model rigorously, certain aspects of nature. Okay, in philosophy, it used to be about beliefs and so on. And then you try and model them rigorously, and then so that you could then use certain rules of logic to deduce certain conclusions, and sometimes even predict something that you might not have known. Now, this particular propositional logic is just captures, like I said, because it is limited to where you have your assertions or your statements expressed in terms of Boolean variables, variables that can take only true or false values, and certain connectives. So they can capture, they're able to assert certain statements of of your environment, of the current world. For example, here, things like this: sky is clear can be captured by this variable, propositional variable clear. If it is true, then it means the sky is clear. Otherwise, sky is not clear. Okay. Similarly, the sky is cloudy can be represented by this propositional variable cloudy, and rainy, and so on. So they're just statements of each of these variables can be used to represent statements of certain of your current state of the world. And then you can make certain assumptions. Logic also provides certain connectives, okay, that you can use to build what are called formulas, to state more complex, make more complex and more interesting assertions. Some of which could be stated as assumptions. For example, if you want to be, that it cannot be simultaneously clear and cloudy, okay, which is reasonable to assume, in nature. So you could state that. So these are Boolean connectives, okay. So you can state that cannot be the case, that is not, that it can be simultaneously cloudy and clear. So in that sense, what I meant that these formulas, they relate these basic assertions that are stated in terms of these propositional variables to make more complicated, more complex and interesting statements. And another one is if it's rainy, then it has to be cloudy. Okay, which means that rainy implies cloudy. So the logic provides a language. The language consists of these kinds of connectives, and then you can start from propositional variables and build your what are called formulas, which represent these kinds of statements. That is the language part of a logic. In addition to that, then you could also derive certain conclusions as a consequence of the assumptions that you make. Both assumptions and conclusions are stated as formulas, okay, which represents certain more complicated statements about your world. So, for example, is it possible to be rainy and clear? Is a question that you can ask if that follows as a consequence of your assumptions. Is that possible based on these two assumptions? Why not? Yeah, but basically you're saying because it's rainy from this, so there is, yeah, that's good. So there is already something that you're assuming about what this equal followed by greater than, which is usually called a logical implication, means. Okay, so that is what is called the semantics. And, not, and implications, they have certain logical meanings. Okay, that is part of your thing. So I never stated what the thing was, but you're right, assuming that they take standard meanings. Then, since you know that if rainy has to be true, okay, first of all, for this to be true, both of them have to be true. That depends on your meaning that you associated with this conjunction. Okay, so I'm saying there is, if you really want to study logic very rigorously, you will have to get into all these. There's a language part of it. There is a semantics part of it, the meaning part of it, which includes specifying the meaning, starting by clearly and rigorously specifying what the meaning of each of these logical connectives are, and from that, what it means when a formula can be true that is constructed out of these things as per the syntactic rules of the language and so on. So you're right. So for this to be true, both of these have to be true. But if this is true, as per the meaning of this, it has to be cloudy. Okay, and 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 since this says that these two cannot be simultaneously true, and since you require, so you have to want clear to be true, so it is not the case. So how about if I did not have this assumption? Anybody else? That's correct. Yeah. So because you could, because there's nothing which says that if it's, so if it's rainy, it is true, but it does not say that it can be, if you allow for it to be clear as well as cloudy, then it is indeed possible. So that's what. So the rules of proposition logic, and sometimes that is part of the semantics part of it, they allow you to derive these kinds of conclusions as by repeatedly applying these rules of this logic. And again, sometimes can be applied as a calculus, okay? They're sometimes called the calculus or inference or proofs of those things. And then that is one aspect of logic. You can also use the rules of logic, embed them inside a procedure, an algorithm, to automate or to automatically check if a given conclusion, a formula in the logic follows as a consequence of a given set of assumptions as per the rules of the logic. And those things are called decision procedures. So whenever proofs are a way of using the proof rules to come up with a proof for that the conclusion follows from a given set of assumptions. These, what I will call decision procedures, are algorithmic way of checking those things. Okay, so both are part of, very much part of the, study of logic. Now, at least here, as I said, I'm not going to get into, so if you took a course on logic, you'll spend a lot of time in trying to define these things. There are various ways you can capture the semantics of logic, different kinds of logics, and how you derive proofs in those logics, and whether, and there is various aspects of completeness, soundness, and so on. They're all very deep theoretical concepts. I won't be covering those things, but as I said, we'll be concentrating on getting you to feel comfortable in using logic to model them and then derive proofs using one of these theorem provers. And the one that we're using is Z3 as a basic thing to start with. Okay, so that's that. I'll take a more complicated example, okay, of modeling for using logic to model artifact and analyze, predict certain things. Okay, this one is a problem where you have 3 chairs, okay, say numbered 1, 2 through 3, and 3 people. And the problem is to come up with a seating arrangement for seating these 3 people on these chairs such that set of constraints are satisfied. Okay, so like I said, so the formulas logic can be used, the proposition logic can be used, in this case proposition logic can be used to model these kinds of constraints. So these are the constraints that you want to ensure that your seating arrangement that you have to derive, come up with, or to satisfy. So person 1 and 3, so these people are numbered also, 1 to 3. Person 1 and 3 shall not be seated next to each other. Every person must be seated in some chair, that you cannot leave any chair empty. That's another thing. and no more than one person shall be seated in a chair. That is, you cannot seat one on top of the other. Okay, so these are, with these, okay, so is it possible to seat these three, one and three? Okay, so say this person is one and this person is three. So, so this is one kind of thing. So coming up with a possible seating arrangement such that these constraints are satisfied. So so how do you do it? First of all, is it possible to is there a possible solution, or there are one or more possible solutions? Anybody? Huh? Yeah. What are the two solutions? Two has to be. So the two has to be in the middle, because that person. So that there are two possible. So let's see how this thing can be modeled in a rigorous way as formulas. Okay. Yeah, these are some questions that you can ask once you have a situation where that have to satisfy. Is there a feasible seating arrangement such that each constraint or a combination of it is met? So what are the possible seating arrangements? Are there seating arrangements that violate fine? You can various questions that you can ask, and each of these things can then you have to model all these things as constraints, okay, and those will be the assumptions, and then each of your prediction or conclusions that you want to check or that you want to get an answer for can be modeled as another formula, and then ask the question if they follow as a consequence of these things, or if they are consistent, if there's a solution wherein your conclusion is consistent with your assumptions. So all these things. So like I said, so for example here, since propositional logic starts with uh, propositional variables. Okay, so the first thing in the modeling thing is you have to express whatever, you have to pick propositional variables, and you're allowed to use any number of variables. Okay, and you have to attach certain meaning to those variables. Okay, so in this case, since what you're modeling is the seating arrangement, so you want to have a set of variables, specifically say xij, where I ranges from 1 to 3 and j ranges from 1 to 3. And this xij will be true if and only if person I, so I stands for the person, okay, 1 to 3, and j for the chair. If person I is sitting in chair j, okay. Now with that, you'll be able to, I'm claiming that you should be able to model all your assumptions as formulas, which are built out of the various logical connectives. That's the goal. So the choice of what variables you choose and what meaning that you attach, and how many variables, proposition variables, that you need to have are decided by what it is that you want to model. And while formal logic in course will not emphasize this thing, it'll study a lot about these proof systems and so on. This encoding aspect is very important, because when you apply logic for, when you're studying logic as applications, the choice of these variables and how you use can matter a lot. Okay, the encoding, don't take it lightly, okay, because how you choose the variables, it will depend on the number of variables that you need to model your problem. And that in itself will determine the size of the formulas. Okay, so encoding is also a very important engineering aspect. when you're using logic to model things in practice. So given this choice, then you can, I imagine that you would have already guessed how you would model the various constraints. So person 1 and 3, the constraint that they cannot be seated next to each other can be modeled like this, right? That x1, 2, it cannot be the case that x1, 2 means person 1 and 3 shall not be. That is x, yeah, this is not of x1, 2 and not of x3, 2. Is it correct? Yeah. 1 and 3 shall not be seated next to each other, which means, yeah, this is basically saying 2 cannot be, has to be at the center. That's basically what this thing is saying. Every person must be seated in a chair, can be expressed in this way. So for every I between 1 and 3, this thing should be true. Okay. So it must be the case that one of these proposition variables have to be true. Okay. So this one is a conjunction of 3 such formulas. Okay. That's what this thing means. So it cannot be the case that all these variables can be simultaneously false. Okay. And the third thing, that at most one person shall be seated in a chair. You know, so I will leave this as an exercise, okay, for you to do, and that could be part of your first assignment to do. You know, so if you, yeah, with these two things, you can exactly see that there'll be no more than one person that will be, and there'll be exactly one person seated in every chair, okay? Yeah, this I've already mentioned. So then you could then say that, so with these 3 constraints, is it to see if a seating arrangement is possible? How will you formulate that? That is, yeah, so that's what introduces this thing. So if you want all these 3 constraints to be simultaneously true, and any assignments of truth value to these variables will be a possible seating arrangement. Is that clear? Yeah. So as long as, so if there is this question, is there a feasible seating arrangement that simultaneously satisfies all these constraints, is one of actually checking if these constraints are feasible, that is, if it's satisfying, if there is an assignment to these variables that makes phi1 and phi2 and phi3 to be, that formula to be true. And that's what is called, I mean, that thing is called whether the formula is satisfiable. You can see now any satisfying assignment, you already guessed that there were 2 possible assignments. They'll represent the 2 possible seating arrangements. So there'll be 2 different assignments for these variables, and they will encode the possible seating arrangements. So that is satisfiability. And sometimes, you know, logic introduces what are called models. So these models are every satisfying assignment to these variables is sometimes also called a model of that formula. A model is assignment that makes a particular formula go to true. So that's what a model is. So if there are more than one model that makes the formula to go to true, then that is what the possible, in this case, they represent the series seating arrangements. So if a particular formula, there's no satisfying assignment at all, then it is called unsatisfiable. In this case, they mean that there is no seating arrangement such that those constraints are met. And validity is sometimes also called tautology. So if a given formula is true for every possible assignment, then that formula is said to be true. So you can ask the question, if is a constraint met by every possible seating arrangement, okay? So those kinds of questions is what these things. So in logic, once these are the three main: satisfiability, unsatisfiability, and validity. Unsatisfiability is negation of validity. Okay, so if validity it's not valid, then it will be the negation of that formula will be unsatisfiable. And that's because of the way that you define negation as a complement of the thing. So yeah, so the takeaway here is that you model constraints. The problem is modeled by as a set of constraints, and that itself involves a judicious choice of what propositional variables, how to select your propositional variables and how to attach meanings to that. And after that, you have to construct appropriate formulas to model each of your assumptions. Similarly, you have to model your conclusion, and your problem, the solution can be either modeled as satisfiability of a particular formula, validity, or unsatisfiability. That depends on what your what your problem is and what is the kind of thing that you want to check. So in this case, it happened to be satisfiable, okay, for this particular problem. As you will go along, you will see that you can also express in some cases what you want to check is actually validity of a thing. If it is you already saw one example in the case of DNA verification. Usually, if you want to show that a property holds good, no matter what input that you use, usually it is expressed as validity. Okay. Yeah, I'm not going to say I have slides here. So today maybe I will introduce informally, and I will get to we'll see. I want to just introduce you kind of informally through examples, and also have Shauryam introduce you to Z3, so that you can actually start working on some examples, get acquainted with Z3, and the assignment, which I will not be grading, this first assignment will not be graded, is for you to make sure that you're able to use Z3 and model, model certain problems using logic, and then check using Z3, that that you can solve certain problems. Either they could be drawn from puzzles, or various things. And that's what I want to do. And therefore, I have slides here that introduces the two aspects, two things, that the components that make a logic: the language as well as meaning and the proof rules, etc., in a very rigorous way. Or maybe I'll get to that next time, or maybe I'll never get in the recap part of it. Maybe later on, just before you read certain papers, if indeed those notations and those things are important, we may get to it, depending upon the thing. Okay. So this is just a way I'm saying, this is, so I'm going to skip through these slides. You have an idea of what a formula is, what the connectivity, how do you build these formulas, and the three notions. Okay. So, but what I'm going to do is to ensure that you understand, and I'm going to skip this. So these examples I will do just to make sure that you understand validity, these three concepts. Okay, so my question is, if I'm going to show you a bunch of formulas, if each of these is valid, is satisfiable, unsatisfiable, or valid. Okay. Let me go through I know some of you, so I'll test the data sciences people. So how about you? And your name is? Sulab? Sulagna, okay. By the way, this formula is in something called a DNF, or disjunctive normal form. You see that it is expressed as a product of sums, where a sum is plus, or here is the logical connective or, okay, which is true if either of them is true or both of them is true. And for an and to be true, both of its arguments have to be true. So any formula that is expressed as a product of sum. So for a product to be true, I'll give you a hint. Each of these, I'm sorry, this is not DNF, this is CNF, okay? Conjunctive normal form, where it is expressed as a product of sum. Each of these is called a clause, okay? And you see that each clause is either a variable occurring in positive form or it occurs in negative form, like it is here. You see the negation only appears at the leaf, okay? And this is a very useful way. Any Boolean function, any function, okay, Boolean function can be expressed in this form. This is something that you will study in a logic course. This is one of the normal forms, okay? So again, for this to be true, because this is a conjunction of a bunch of what are called clauses, which are disjunctions, each of them has to be true, correct? So, yeah. Yeah. And what is the satisfying assignment? What is a possible satisfying assignment? So you have to. Yeah, okay. X1 for this, so X1, so if X1 is true, yeah, X2 has to be false, and X3, so then once X1 is true, you don't care about, for this to be true, what X3, so these two can be made to be true, okay? But there are other possible satisfying assignments as well, yeah? See, I picked something that was different than than yours. Okay, and this is sometimes a kind of the notation that is used. This is model of the formula, in this case, satisfying assignment, and this is says that this particular model satisfies the formula. We started at 10:30, so you can go till 10:45. Okay, so stop at 11:30, and you can at least go through one example. Don't worry, I mean, we will have one more class. Okay, so we'll finish all the examples through that through next time. Yeah. Satisfying means you have to find an assignment, a truth assignment. When I say truth assignment, either 1 or 0 for each of the variables that makes the formula go to true. Yeah. Yeah, it is satisfiable if there exists one assignment, at least one assignment, truth assignment to the variables that makes it go to true. So it is valid if every possible assignments, if the formula has 3 variables, you can have 2 to the 3 possible assignments to the variables, correct? So it is said to be valid if it is true for every possible assignments. Okay. And if it's unsatisfiable, if it is false for every possible assignment. So they could be, if it is, you can have formulas that are neither valid nor unsatisfiable, because there could be some assignments for which they're true and some that make it go to false. So the question was if this is, so this is certainly satisfiable. Is it valid? If, yeah, this one, yeah, the validity question, you can think about it, you know, you will have to find a unsatisfying assignment, then then it's not valid. So to check if it is unsatisfiable, you know, one way to do is you check for every possible assignments. Okay, that's of course is there should be a better way of doing it. Okay, and this is a side note that I will do here. This satisfiability question for proposition logic itself is quite hard, and it is one of the typical NP complete problems. So it is quite hard. So there always be some instances where you may, the best known algorithm will have to consider all possible assignments. Yeah. Oh, in this, yeah, there's probably a mistake here. Yeah, there must be, I think at the very end, is it? Okay, so that's what makes it, if X, probably, if X is true, but how about if it is here? Ah, okay, I don't know what the answer I have is. Yeah, I have it as valid. So if it is, yeah, I think it has to be here, correct? Yeah. So if X is true, and then the assumption is there's a thing here as well, okay, and this whole thing, and then it becomes valid, because the moment X becomes true, and because there is X here, it becomes valid, and so on. Okay, so you get the idea. So this is important, yeah. So for you to understand, so this is something that is not that is unsatisfiable, because no matter what assignment you make, there'll be you won't be able to make something else satisfied. So for this to be true, the C has to be false, okay, because it's a conjunction. If C is false, then so in order to make this, B has to be true. But if B is true, you have to A. But then, so there's a like a circularity in there. Um, um, yeah, I mean, there are things here, but what I want to go in the thing, maybe there are lots of things in here, but I want to quickly go to this. Okay, so here's another one. Well, I'll go through two more examples, okay, and then you can, maybe show one of those things as a starting point. See, this is another kind of situation where it's quite popularly used, propositional logic to model. But it's configuration management, deciding if a component can be installed, okay, whether you want, this could be software component, or whether something is implementable or not. And there are various constraints. So here, this arrow means in order to use A or to implement A, to install A, you need all these three components, okay, because it depends on all three of them. So this yellow means it's already installed, okay? And this, dark circle here means in order to install C, you need, this is an and, this is an or. You need either of them. And you can't, maybe because of some size constraints or something. They may, there's a constraint that there is some conflict between them, and you can't install both of them simultaneously, okay? And the question is, so with these constraints, is it possible to install A, okay? Yeah, the goal is to install A. Z is already installed. And the question is if it is possible to install A with maybe, I mean, you can impose the other thing too. If there is a possible way to install and then you can add this thing by installing the minimum number of components, those things can be added as objective function. So if there is even a possible way to install is what I'm trying to model here. So once again here, you have to separate between, so here the propositional variables are kind of fairly explicit, right? What you choose. So for each of these components that are shown here, you can have a variable that denotes a proposition variable that denotes if it is that it is either installed or not. So, and these constraints that are shown here can be need to be modeled as propositional formulas. So it says A, in order for A to be installed, you need B, C, and Z, and so on, and so on. Finally, so this constraint can be modeled as, yeah, it cannot be the case. The D and E can be installed, both can be installed. So that's what this thing is expressed in a, as a disjunction. And your goal is you want A, and Z is already installed, and you want to check if A can be installed. So any satisfying, in this case also, any satisfying assignments, if there is one, is a possible solution to it. Okay, maybe you could, I don't know if this thing is typed in or not, but anyway, you can choose whatever that you want to demo. So you get the idea, right? So once again, this installability problem of a bunch of components in a configuration management based on to satisfy a set of constraints can be modeled. This robotic planning and all those things can be modeled as a set of formulas with certain assumptions, and then you can use the Z3 kind of thing to come up with solutions that are quite commonly used in practice. Now, the question that I'm raising is if propositional logic is enough, okay? I mean, so let me go straight to this DNN since we are using DNN. I mean, as an example, so obviously propositional logic will not be enough. Now, if suppose you want to model, it's a simple DNN. You've already seen DNN, what exactly a DNN does and what it is from Diganta's lecture. This is a very simple DNN model. Firstly, can you model this using propositional logic? I mean, assuming that each node, the activation function is a ReLU activation function. Introduce ReLU, okay? That's why I asked the question if propositional logic is expressive enough, if it is adequate. By adequate, I mean if it is expressive enough to model the behavior of this DNN system. Firstly, what does it mean to model this DNN system? Anybody? Well, I'll give an answer to this. I want to model what the output is as a function of the inputs. Okay, I want to, as a formula, I want to construct a formula which defines, which characterizes. Okay. See, after all, a formula in propositional, as I said, is constructed from a bunch of variables. So I said that propositional logic, so a formula can always be used as a Boolean function, okay? So each of those formulas that I showed you in that is a Boolean function. In what sense? So it can be considered as defining or characterizing a function which maps the set of tuples, where each tuple represents an assigned assignment, okay, a truth assignment to whether it goes to true or false. Okay, so that's in that sense, a formula represents a Boolean function. Each preposition formula represents a Boolean function. You understood that now? So it for every the input, the domain is tuples, the set of all possible assignments to the variables, and the range is 1 or 1 or 0. And whereas here, what are the inputs? What are the inputs range over here? If you want to model this, okay, you can model this as a relation between the output, which in this case is a real number. Inputs are also real numbers, okay? In this case, there's only one. In general, in DNN, it'll be a vector. So that's not, you can have, functions vector. And by a relation, you mean, what does it mean to model that as a formula? I'm modeling it as a relation between the output and input. And that formula will be true if this function is 1 or 0. So what I'm asking is, if there's a way to construct a function DNN as a formula such that, this should be constructed as a formula in some logic. So I'm asking you if you could model this in proposition logic such that this will be, true for some specific x and y. Okay, so it will exactly define. That's what it means to. You have to construct a formula in a logic. In this case, I'm asking about if you could do it in proposition logic such that every input-output pair for which the formula will be true will exactly correspond to the output that it returns for the corresponding inputs. So the question I'm asking is if you can construct a formula in proposition logic to do this. Okay, the answer is, okay, well, it kind of depends on the thing. Firstly, these variables are ranging over real numbers, okay? So if you're really interested in characterizing a formula, the function, over all real numbers, the infinite set of real numbers, you won't be able to encode that using discrete number of propositional variables, because the propositional variables can only take 1 or 0. So any tuple of variables can only encode a countable number of elements. Okay, so whereas these are infinite sets, in this case, real numbers or even dense integral sets, because between any two numbers, there can be infinite number of elements. So that is one. Okay, one is that you won't be able to, you need logics that allow you where the variables in that logic range over more expressive domains, more complicated domains. They cannot be just 1 or 0, such as numbers, real numbers, and various other things. Okay. And I mean, that's the thing. And another thing is sometimes, in order to, the question will be if you can always capture, you remember that, these functions, if you can be able to encode all possible computing functions, computable functions, okay? So then one thing that you noticed in this proposition logic was there were just proposition variables and there were no something called quantifiers. You can't say if for everything, if there exists something, okay, these kinds of quantifications. Those two are what characterizes. Now, in this particular example, okay, so that's where propositional logic is not expressive enough, and you have to go to more sophisticated things, and two ways in which, and that's the next more expressive ones. The one that is a logic that is more expressive than propositional logic is a first order logic, and what distinguishes that is two. One is it allows its variables to range over domains that are, other than just discrete Boolean domains. The other thing is it allows quantifiers, and the ability to, and it allows to have functions in them. And that's what first order predicate calculus, the logic of first order predicate calculus thing. So now, in this case, let's suppose that I just allow, yeah, so Z3, it supports so you can extend this satisfiability, validity, and unsatisfiability notions. You can extend that for first order predicate logic also. And Z3 supports not only proposition logic, but also first order logic. Now, I'm going to quickly go through how you could model this one. And you can do that, this one, by just extending the, allowing the domain to be real and, without quantifiers. Okay, so let me go back. Okay, so here it is. So for a moment, let's assume that these variables are ranging over real numbers. Okay, so then, with or without quantifiers, once you allow for the variables to range over more sophisticated domains and even infinite domains, you are moving away from proposition logic. That is one observation that I want to make. Now, how can one model this? That's the question that I'll quickly go through. And once you allow for the more real domains, this is pretty much okay with equality and a few other predicates you'll be able to model. So I'm assuming there is a ReLU in each of these layers, so that I'm splitting them into two nodes here, the backward and the forward node. Okay, and there's a ReLU in between, and similarly for the output node also. So what we need to do in the problem of modeling the behavior of this DNN is one of defining each of these values of these variables, which denote the value that at the input and the output of each of the neurons, okay, the hidden neurons in the thing, in terms of your input variables, or you could define the value at each layer in terms of the layer before it, okay, which is what I've done. So I've extended these things. So VN1 defines the input, denotes the input. This is the back, and this is the front connected by a ReLU. So V21B, as you know, is just a linear function of its input. In this case, V21B is equal to V11, correct? Yeah. And similarly, V22B is minus V11 because the weight thing. So this can always be the backward values, the backward at the input to each of the neuron can always be described by a linear function, okay, of your input. And here minus, plus, etc. are operations over real numbers. They're not logic. I mean, they're not Boolean proposition logic anymore. That's why I'm saying you're moving into the domain of first order predicate logic. Okay, like I pointed out, it also allows all these functions, okay, these operators over those domains. Now the ReLU function requires, can only be, you need the logical connectors for doing it, because that is like an implication, right? Its output, V21F, is dependent on whether V21B is negative or positive. That's what is non-linear in that way. And that non-linearity can be captured in terms of by splitting, which is what Diganta was saying. So you can split it into the two linear portions of it. And that's what is being done. And I'm expressing it as a implication here. It's a conjunction of two cases. So the first case is V21B being less than 0, in which case it'll be the output will be 0. Otherwise, it'll be equal to the input. And that's the structure I use at each of the neurons. In fact, that I've repeated that here and in here to define the ReLU output at each of the neurons. Okay, and then finally V31 F, where I have it defined. V31F is defined here conditionally. So this is each of them. So a conjunction of all these things put together gives all the constraints that define the function computed by the neural network. Do you agree? Because as I said, I'm defining it as a function because it, for any pair of values, V11 and V31 of F, that makes all these things go to true, will be a legitimate input-output pair of the function that DNN, that is consistent with the DNN behavior. You can, yeah. Am I taking care of? For each node, am I taking care of what? The weights. That's right. No, here, yeah, you're right. Here I'm assuming that the bias is 0, okay? But you can see that you can take care, that can be taken care of by the way that you define this, okay? So here, it will be some linear function. That's what I said, some linear expression. So in general, it will be a linear combinations of the values that are coming out of these things, and if there are more multiple ones. So I'm kind of hand-waving. In this case, it's a very simple thing, but as long as you allow for all the operators on real numbers on the domains, you can always express, you can replace this with an appropriate linear expression that is a function of the weights and the bias. Okay, so in this case, the bias is 0. And the weights, since are 1 and -1, I'm just embedding them in that thing itself. Yeah, yeah. So what is this you're saying? Yeah, yeah, I'll get to that. This one. Yeah. So this whole thing, which is a conjunction of these things, will characterize your in the function that is computed by DNN. In the sense, it actually defines it for all possible inputs. Yeah, the output that is generated. Now, in this case, this satisfies this output. The output that it returns satisfies this this particular property. Okay, it's almost identity, except that it can be yeah. If it is negative, it never gets passed. Okay. So therefore, it is always the absolute value of the input. Yeah. Do you believe that? Yeah. Okay. And that's what this thing is. Something that I want to check. Okay. And that can be checked by checking the validity of this input. Okay. Why validity? Yeah, that's right. So you will have to be tested if you want to check if it is true for all inputs. So there is an implicit thing in here when I don't say, technically what I'm saying is for all V11, this should be true. Okay, actually for all V11, V22, all these variables. But V11 is really the free one here because all the rest of it are dependent variables because they are defined in terms of the inputs in a nested way. So it is enough to have for all of those things. But in general, it means that they're all universally quantified. And if your goal is to verify that this input-output property that I'm saying for all inputs, then you should check the validity. Now, there is always, maybe I don't know if you'll have time. Maybe we could take a simple example and do it. Yeah, I'll be done with this thing. So satisfiability is also is useful even in this case, even if you want to verify the thing. So you can ask the question: if there is Yeah, if there is a satisfying, I mean, if this network can produce an output, say 0.5 for a negative input. If so, what is the negative input? Can it? We have already established that it can only its output is always greater than or equal to 0. Okay. But now I'm asking the question, if there is an input for which the output, a negative input, okay, is there an instance of a negative input that makes the output 0.5? That, is there one? There's a negative 0.5. So that can be posed as a satisfiability problem, okay? So you can extend this, okay? Is there some output within a certain range, is, which inputs that are constrained to be in a certain range that produces an output in some other range, okay? That would be a very useful thing. The robustness property was actually defined that way, that Diganta showed. So that can be posed as violation of these robustness properties can be posed as a satisfiability question. So that's where, so that thing will be important. So so I want to stop there. So, and next time I'll introduce some symbols and so on. So if you could, I don't know, 10 minutes, yeah? Just so, I want, even if they don't think, so how to invoke Z3 and do a very simple. Yeah, I don't, just use GUI, yeah? I don't think that is necessary. Oh, if you could join onto the meeting, then this is good enough, yeah? The Zoom meeting. What I'm going to have him show is, say, I want at least the people who are undecided and you really want to, I mean, even people who are decided, if you want to get started on Z3, okay, that has that the GUI interface at the web link that he's going to show already has a lot of examples and you can get started with it, okay? But I will, at the end of today or early tomorrow, we'll give you a bunch of assignments. So if you can get through with that, then I think from my point of view that I think you should be able to handle the course, with the caveat that you should be willing to put some effort to actually read the paper and go beyond reading some supplementary material to the paper. Okay, so that's the thing. What? I have to make you co-host now. I guess you have some constraint. That's okay. Stop sharing screen. Or I can make you. The link for that using it without actually downloading anything, just using it using the interface. I've already included in the lecture schedule as a link. Just click on that, and there is simple copy to get started. We also show some examples. You can try give an example of any. I
Two functions which basically take an integer. Because there's somebody else on the other side. So I have two functions which take in an integer and then just basically return the square of it. Function f takes z as y as x as z, and returns x into x. So this also returns y square, this also returns y square. And now we want to check if these two program functions are equivalent or not. So we need an assignment y such that fy does not equal gy. If this is an unsatisfying assignment, then we know that fy equal to gy is valid. And if this is valid, these two functions are equivalent. So these 6 lines just basically encode what the timestamp variables are. X0 is the first time x has been used, x1 is the second time x has been used. So just declare the constants and then assert that z1 equals y0, y1 equals x0, x1 equals z1, and then r1 equal to x1 times x1. This uses Lisp. I'll show you how Lisp works later. That's multiply. And yeah, but not in the 3. So and R2 returns y0 times y0. I'll show how the syntax works later. And I want to know if R2 and R1 are always equal. So I assert the not of this and then check if this is satisfiable or not. So there's no assignment of x0, x1, y0, y1, z1 such that r1 and r2 are not equal since it's unsat. Therefore, r1 always equals r2 and f and g are equivalent functions. Proving the equivalence of these two functions. And this returns unsat, so both of these are equivalent. Yeah. So these 6, you can just declare a function constant Boolean. This is the name and what's the type of it. If it was a function, I would use declare fun, then the name, then what data types it takes and what it returns. So suppose f int. I declare all my variables here, and I'm changing my variables every time. Like I'm changing z, then I'm using x and z. So I'm using timestamps as my variables. Every time I use a variable, I use a new timestamp. So I declare these. These are just the constants in this domain. This can be integer, rational, Boolean, or whatever. And then I'm just asserting that these have to be true. Z1 equal to Y0, Y1 equal to X0, X1 equal to Z1, and X1, R1 equal to X1 times X1. So it just creates that F function, and this creates that G function. So I'm checking if there is this assignment such that F does not equal to G with this. And since this is unsat, then there is no assignment Y such that Fy does not equal to Gy. So for every Y, Fy equal to Gy, which means it's valid and the two programs are equivalent. So Lisp works like as operator AB means A times that operator, A operator B. So equals Z1Y. So if I change GY to be Y plus Y, then I get X0 as 0. Wait, just Y0 as -2. So if I have -2 as my input to Y, then F returns me, sorry, 4, and G returns -4. SAT, you can return the model and it shows you what the assignment was for each number. I'll show the API next class with that example.
give some small set of decision procedures that are relevant for giving information. Yes. Does that answer your question? Yeah.
Can I show the 8-pin example with the API next class?
Yeah, I think you can do that. Yes. I think in next class, what I think you should go with the examples first. That is perfect, and we can give them maybe that's a purely Boolean example. What I would start with is some simpler examples that they've actually seen. Maybe show the two examples, the seeking problem, as well as seeking problem is they've already shown that.
I'll show that.
And then say, do this. Okay? And there, the API, you need it, right? Okay? So, yeah, you do that. Then I will, if there is time, then I will do a little, then I will do this class. Even taking one more class for the last week, it might be worth it. Yeah? Because when they read these papers, they will need it. Because those papers will assume even mutation is there. So they will need that. So that's why going slow with the thing is good. Conceptually, that they're able to understand that part is not required. So that is important that they go through step 3. You can even show some you can show annotation thing with it. You look at my slides, and there are programming examples that I can go through, before you use. I'm studying finish. But make sure that you run through the example. And anything, for example, it's just as a feedback. You showed me that's the first time we're seeing is one of the things that you should tell them. You put very obvious. You didn't say anything to the fact that okay, use this species. Yeah. So okay. Any program has this first and up down approach. Say that. Okay. And then you do this. Again, there are commands, check stats, pretty clear. That is what is missing. Okay? And if you can use more important things, try so I want to make sure that they see small examples. Okay? That before you go into API and the end, you should use the two Boolean and transitional examples that we discussed. And you've already shown this one. I would like to have shown transitional examples. Okay, so there, yeah. Have really advanced that sense. An interesting thing is really shown is that someone who wants right ahead. Someone it is independent of what that function does. But if you want to do that, you get the unexpected function. Maybe that's too complicated. What that you should see is a good example. That's the last one. That is something I should have because I already made that. I think therefore I said that maybe you should find out. Usually it does not. Since it does not, then my only the last time yeah, the way it is defined is between 1 F and B are both positive. Yes. Anyway. But the reason that I actually don't need the value there at all, not in this particular case, that's what we achieve. I mean, as soon as I did that because I had the formula with the value. And the formula had a value there. That's why. Yeah. Yeah.
I started learning like this predictive calculus and professional learning in Z2 before and from a book, and then I got interested in course. I will not be crediting auditing, but I would like to make a report on the whole course. And if I am able to do something new, obviously I'm not gonna do something totally new because in 4 months is not possible. I will do something.
What do you mean you want? I mean, why don't will you be attending all the classes vigorously? Huh? And then you said you want to do a report. Okay. What does it mean? I mean, if indeed you want to attend and you want to learn something out of it, why don't you read the papers? I won't grade you. Yeah. Why don't you read the paper? And that will be your, I mean, if you want to write a report, for whom you want to write a report?
Just for myself, I can write a report or something from out of course I can add something.
You're an MS student, is it? In CS?
CS first year.
The first year. You had a logic course?
Yeah, I am doing a logic course.
You are doing a logic course right now. With the same class now.
Yeah, I will be going soon.
Okay. No, you can do that. But what I'm suggesting is that you should, yeah, I'm okay. In principle, I'm okay with it. Okay.
Yeah, I was just wondering if you can review the report.
Yeah, that I can do. But rather than you writing a report, I mean, you can write the report. What I'd rather you do is read. I'll assign you a paper and you present that in the class. If you're willing to do that, then I don't, yeah, I mean, independently I can read the report. Yeah.
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 Just